So the next presentation, I'm very glad, addresses, I think, one of the shortcomings of what we've heard so far, which is the technology options and technological choices for ultra-low NOx. Charles would have covered this earlier, but in his absence, I'm especially glad that Mike's joining us. Dr. Mike Geller joins us from the Manufacturers of Emissions Control Association, that's MECA. We've heard about MECA earlier through the work they've been doing following with Southwest Research's Phase 1 project. Dr. Geller serves as Deputy Director of MECA. Before joining MECA just a year ago, he worked for 7 years at the Office of Transportation and Air Quality in the US EPA, where he was an environmental engineer focusing on transportation policy, including an emphasis on domestic and international black carbon and science and policy. He's had more than 15 years of experience in issues related to air pollution from mobile sources, both regional and federal agencies. And he spent some time as a research professor at the University of Southern California. So very glad, Mike, that you're joining us. You're going to be giving us a review of ultra-low NOx reduction technologies after 2025. So some of the, certainly the issues we've discussed earlier in terms of the choices that you see might be coming up down the road with when we get down to those really low levels and the impact that'll have on the engine efficiency. So floor's yours. Thanks for joining us.
Thank you very much for the kind introduction. Thank you for having me. It's great to be at Integer. It's always nice to come to Pennsylvania. I'm born and raised in the state, even though on the other side. And it's good to be in Pittsburgh again, although it's interesting that everyone still calls it Steel Town. You can see that it's made quite a renaissance in a bunch of other areas now, and it's hard to walk outside now without seeing autonomous Ubers driving around everywhere you go. So I think they might change the name in the future. Thank you very much. I am going to speak a little bit today about some of the work going forward on developing technologies to get to ultra-low NOx emissions levels from heavy-duty engines. I'm going to start with sort of some of the work that's a little bit of a summary of some of the work that's been going on down at Southwest. Obviously, refer you to some of the folks down there to get a more in-depth version of that story, as well as some of the slides that ARB has on their webpage, since they're the primary funder of that. And then I'll kind of go sort of towards the back end of that, which is what's enabling some of those technologies and where we're going. All right, so this is my standard opening slide, just to introduce the Manufacturers of Emission Controls Association. The center of this graph is the engine, and the members of MECA are suppliers of a lot of the technologies that are all surrounding this engine. About 4 years ago, when MECA was founded, there was a large focus on criteria emissions. That was the style of the day, and it was right when EPA was starting their emissions regulations. It has grown to an organization that includes also efficiency technologies to gain efficiencies in the engines through air handling, like turbochargers and EGR, a number of systems from integration of those catalysts and coatings and substrates, which is some of the original focus. There's some sensors, of course, as we've heard some talks earlier about the expansion of OBD through regulatory means. And electrification, which was just noted in the last discussion as we go towards some 48-volt type systems, including waste heat recovery. And of course, you can look at inside the cylinder. We have some members who look at fuel injection type components and evaporative controls as well. All right, just make sure that I'm seeing the same thing you're seeing. It's a little bit chopped on the one side, but I think we can see what's going on. But some of the work that's going on, as you can see, it was noted earlier today that some of the systems that were put in place starting in 2010 to get to the current emission standards for NOx was this system that had the SCR and the DPF sort of in this series train. It was repackaged pretty early on to get sort of this idea of this one box type system. And then if you look down towards the bottom right of this graph, you can see that there's this a smaller version of that as we can start to collapse some of the systems and get to systems that might have some SCR and filter type devices, or even just more efficient catalysts and substrates as we have better manufacturing of those processes. And then, of course, if you go down to follow that diagram over to the left, you'll see that this is where we're trying to head for in the 2024 timeframe, which is a much compact device, which does have this implementation of an SCR filter, possibly a passive NOx absorber type of system up front that also includes a DOC. All of this has been basically a natural optimization that we've seen throughout the number of years that we've had experience with these systems to get a 60% smaller, 40% lighter, and of course when you save some of those materials and you get not only a space savings but money savings, and also it helps with thermal management. So we can get to a point where we have better optimization of our substrates, better optimization of catalyst coating, and we also have calibration strategies that have come a long way. All of this comes together to have a nice small system closer to the engine in some cases, faster light off, all the things that we've heard discussed as we tried to go toward an area of getting to the goals of some of our customers, which are the regulatory agencies in this case, that need lower NOx standards. This is one of the data compilations that we've pulled together over a number of years, just looking at what's provided on EPA's certification database. We just looked through the systems that have been certified over the last, it's about 15 years now, to see what they have been certified to in terms of their NOx and CO2 standards, or emission levels, I should say. And because we've had a little bit of a step change in the early years, it wasn't as easy to do the optimization because a lot of the systems and engines that were put in place had to meet a standard of PM first, and then the NOx standard was later, and then of course CO2 was its own set of standards. So trying to do all those separately is not as easy as if someone gave you all the criteria of those emissions at the same time, and you can optimize those engines with all of their systems and emission control systems at the same time. You can see the trend that we see is the yellow diamonds there, the open yellow diamonds, are 2017, and those are going down towards the bottom left, and the trend is that you are able to get better efficiency, lower CO2 emissions at the same time as reducing NOx. In 2017, just from a count of the 36 diesel engines that I saw on the list the other week, there were 11 that were certified at or below 0.1, which is clearly better than the half the standard now. The lowest NOx cert level was as low as 0.05, and this again is a diesel engine for NOx. And then I looked at the pair. There's a vocational engine that was actually certified down to 0.06 gram NOx engine and 496 grams of CO2, which is already meeting the standard for phase 2 standard for 2027. So just a few words to talk about the technology demonstration program that was put together by California Air Resources Board, funded by them, and then a lot of the test program was conducted down at Southwest. MECA provided some bits of funding, but also some of the emission control strategies that have been put onto the systems down there. The whole reason for this, of course, that was mentioned nicely by Bill earlier, when he also called me out, was to say that their goal is to hit 90% reductions, I think, from this sector, basically. And they're trying to meet their ozone targets, which are slated to come into effect in 2023 and 2031. These are current ozone standards, and then there's also, not to mention the ozone standards that are sort of on the books at EPA that were passed in 2015. They're even lower. So there's definitely a need to get to lower NOx from California's standpoint. Not to mention there are plenty of other states around the country that do also have ozone problems. There are states up in the Northeast who have also adopted California standards in order to meet their air quality goals. The target is a 90% reduction from current standards, as said. 0.02 would be the number then, and the solution that was supposed to be put together needs to be consistent with this path toward also not having an impact on the climate change aspects or the fuel economy, basically. So the CO2, of course, we shouldn't see an increase in the other climate pollutants like methane or nitrous oxide. Make sure I'm on the right thing here. The test cycles that were implemented, a majority of the testing, the primary focus was on the current certification cycle, which is the heavy-duty FTP. There was also some testing done on the World WHTC, World Harmonized Test Cycle, and then there's also the RMC set, which is commonly used for the line haul sort of steady state certification for a CO2 type standard. And that's for greenhouse gas assessments. There's also some idling work done. Their additional vocational cycles are also interesting. Of note that ARB is interested in is looking at trying to find what's going on with the low load test cycles to address some of the vocational things, vocational items and vehicles that are operating in the real world, and how to get at low NOx emissions from those in use. The New York bus cycle was looked at. There's an ARB creep cycle, Orange County Transit Authority cycle. Also, some other low-load work is being done down at Southwest in their Stage 2 element that Bill talked about earlier. So the program engine that was selected for the first part, Stage 1, is the 2014 Volvo, which is a turbo compound engine. It has cooled EGR, DPF, and SCR. You can see the characteristics of the engine on this slide. Volvo had put this forward as a plan for future engine development, as it has the ability to recoup some of the heat, the waste heat in the exhaust, and basically drive another shaft to get mechanical energy from the turbo compound unit. Of course, that also results in some lower temperatures in the exhaust, which we'll discuss in the slide coming up. The other engine characteristics here are there's no tailpipe ammonia, and the N2O was around 0.05 grams per brake horsepower. As noted, the challenges with this engine are if you look at an apples to apples from a model, the same model year or same model of engine from 2011 versus this 2014, you can see that the temperature trace here is significantly lower for the 2014 engine when you run it across an FTP cycle, specifically early in the cold, and it takes a while for it to warm up past around 200 degrees Celsius. The other challenge with this system is that there was no real way to bypass this and to work around it in this current test program. So we, and I think some of the folks who were a part of the advisory group, have viewed this as sort of our worst case situation for what the challenge would be to operate on an engine and try and get the fastest light off possible for at least the cold start part of the cycle. So the first step that Southwest spent some time on was to look at recalibration of the engine to get faster temperature heat up at the beginning of the cold start, which is one of the challenges, of course. They modified the existing engine calibration during warm-up, and then this would, of course, help with the light off of the after-treatment system and get the NOx reduced faster. There's also some modifications that they did to EGR. Some multiple injections were done, intake throttling, and elevating the idle speed in order to get warmer temperatures throughout. I guess I can use my laser here. So this is all being done early on. So we have the baseline here in black, and then early on they're using these strategies to get faster heat up inside the engine and the engine out exhaust. As you get closer to sort of this middle point in the cycle, the temperature is basically at the point where the engine would have been at in its normal operating condition without any changes to the calibration. They can then get a little bit back and sort of push the engine a little cooler and play with a few things to get, I guess not cooler, but play with some of the things to get more fuel economy out of the engine then, because they can release a little more NOx that would then be taken up and converted by the after-treatment system, the NOx system that is now currently fully warmed up. So that is shown sort of here, that we have, this comes up and the NOx then, baseline calibration has higher NOx, the new calibration is down lower. And this is, of course, this is engine out, I should say. So not to get everybody worried that they're the same amount of NOx at the after tailpipe. This is just the engine out conversion. And this is what I was just talking about with getting a little bit of the efficiency back, fuel economy back when the engine's warmed up or when the after treatment is warmed up. Now that you have this system is releasing a little higher NOx, but of course that's going to be converted in the emissions control. So this slide, I just wanted to illustrate that there are a lot of ideas, there are a lot of actually potential solutions to this problem of getting to lower NOx emissions out of these engines. I know that we've seen a couple of the approaches, at least we've seen the final approach that was chosen, and I wanted to just reiterate that we were a part of a test program that basically had a defined timeline and said we have to meet these goals, let's bring a bunch of ideas together, see which ones are going to be the most feasible. Ultimately, we can only select one because of time constraints and funding. Even though we had a few other options that looked like they were promising, we also didn't have, or Southwest didn't have the time to really do a lot of the engineering work that may have needed to be done to get some of those tested in the time frame that they needed to do the work in. So you can see here that there's traditional and advanced approaches were divided here. Some of them involve adding heat. You can obviously add heat from some of the ways that were just talked about by Jeff, through the burner, through some electrically heated catalysts. You can also add heat through the dosing. You can do that to either of these style of approaches on the left or the right, the left being what we currently see in today's systems with a DOC, DPF, and SCR, and the right being this idea of putting some passive NOx absorbers with a DOC in front, maybe putting some SCR in front, having SCR on filter, and then maybe having some SCR downstream, a second SCR downstream of that. So there's a number of ideas that were put together. The one that was tested, of course, we'll talk a little bit more about. I think this was one of the charts that someone was asking a little bit about earlier that Bill might have wanted to show. It shows a lot of the differences in the systems and where we can get to and how many ideas were put out there. And you can see that with traditional systems and adding some of this additional heat and with the engine calibration, you can get, go back. You can bring this down. Of course, as I mentioned earlier, we've seen some engines that are already certified down in these levels in this region right now. And then when you get into adding low temperature enablers, you can get down here, which would be like heated dosing and adding ammonia instead of urea. And then you can add even more with a burner or an electrically heated catalyst with some supplemental heat. There are quite a few systems that are really around this range of the target that were basically looked at towards the end of this before down selecting to that final configuration. And this is also shown, I think, in at least 2 presentations today now. The final configuration that was selected for testing, of course, has this passive NOx absorber with DOC combination, this mini burner that adds some supplemental heat as needed when the temperature is below a certain threshold temperature, and then going into dosing with diesel exhaust fluid, and then SCR on filter, a SCR, and ammonia slip catalyst at the end. So in here, you can see that when they tested this system, they looked at the cold and hot FTPs with the engine out and with the tailpipe after testing, which was the development age parts that was referred to earlier as testing with some of the mini burner system, or not the mini burner, the burner system that Southwest uses for their modeling. Got down to these really, really low levels across the cold, hot, and composite and RMC set cycles. So, of course, the cold cycle is going to still be one of the higher NOx emitting parts, but when you do the composite, you get down to composite number of 0.012, and the set, ramp set, 0.015. Another cycle that was looked at was a vocational cycle, and this was the New York bus cycle. And here, and really the conclusion here was that when they ran this cycle with the ultra low NOx system, they got down here, and you could see that your tailpipes out was very, very much lower, with an 85% about reduction in NOx by using this system on a bus cycle. And I would go over all the lines, but it's all very quite muddled up there, other than to show you that you can see where the temperature is increased with the added heat right here in this red line, and that's what provides this ability to get at the lower NOx levels of this configuration. So that's what I'm going to say about that program. I also just wanted to kind of switch gears and shift into the reasoning and why we see a lot of promise in this area, and why it's not just one solution. It's a number of things that are all working together to get to this goal. The first one being that substrates are ever increasing in terms of their ability to be more durable as well as more effective and more efficient. One of those is the goal of substrate manufacturers is to get at a more uniform pore distribution. As you can see in this slide, some of the older ones had a little flatter distribution, and some of those pore materials had some bigger pores and smaller pores mixed together, which provides a little bit of an issue with losing some of the filtration efficiency if you have some of those larger pores, but then you have the really small ones that really has a problem for getting some uniform coating of your catalyst. So when you make the uniform pore distribution, then size distribution, you can really get at this really nice ability to coat and have more efficiency of reducing your materials you're trying to trap in there. Of course, this also allows you to downsize the catalyst in volume if you are more efficient at doing all of this, which gives you ultimately a better way to have less thermal mass so that you can really heat that up faster, which is really a really good goal of a lot of this work. The other note, of course, is that this is always a key that was mentioned a couple times, is lower pressure drop is going to get you a benefit from pushing back on the engine, and of course save you some fuel. Another graph that shows some of this information is presented here, which is basically saying that the next generation substrates for both DOCs and SCR are reducing that back pressure that I was mentioning and fuel consumption. If you look at some of the older versions of these substrates that have larger wall thicknesses in terms of the pores, so 6 mil thickness between the pores, and also have between the cells, I should say, and then also have less cells per square inch, you can get less coating on those and also have more back pressure because of the way they're designed. And the ones on the right here, that I keep hitting the arrow instead of the laser, you have much thinner walls here, better thermal management so you can heat them up. You also have better porosity, so less back pressure through these than through these standard substrates. And the graph illustrates that by showing that you have better conversion of hydrocarbons through these more efficient substrates as you get larger in terms of your cell density, and better your wall thickness is decreasing. This is some work I should caveat that I'm cultivating a lot of, or curating a lot of other people's work. So I'm bringing in a bunch of slides from people that are doing this work and presenting it. So there's some presentation that was done at the by some folks that were funded by DOE, and they do their annual merit review, just to show that this isn't a stationary point that we're looking at. A lot of people have traditionally said you need to get to 250, you need to get to 200 degrees Celsius to get your light off from your catalyst, but there's a lot of work ongoing to get to lower temperature catalysts that can work in this low temperature regime. And this is just one example of that, where there's a goal of getting to a DNOx target of 90% at 150 degree SCR temperature. So there's a consistent evolution of the technologies as we move forward as well in all phases. Another piece of work that's been presented at some SAE at the World Congress earlier this year, I guess, was just looking at SCRFs. There's continuous development in this area, since this looks like to be one of the more promising technologies as we go towards lower NOx. And really just some work that was showing that if you quickly load these and force regenerations over faster than they would normally happen, and see what the impact would be to regeneration on these catalysts that are on the SCR or on the TPF, that you can see no real degradation of that. Presumably, as this is happening, you're also getting accumulation of ash. So the ash accumulation itself, as well as you move to the right with these number of regen cycles, is not causing a reduction in actual performance. The work also did go on to show that after doing a normal cleaning cycle, they also had the same conversion rates after that. This is just a note on the ammonia slip catalysts that are also being continually optimized. This work really just the point here is to show you that there's a higher selectivity towards the nitrogen and a lower selectivity towards going to making N2O make at the end of an ammonia slip catalyst. So you obviously want to reduce that and get conversion. So this graph over here is really just showing you that there's a much higher selectivity of these green, newer versions of these catalysts versus the older ones that were the yellow ones, and that you have lower N2O make. I think I'm only getting close to the end here. Make sure I'm not too far behind schedule. Yeah, the last couple are really, one of them I noted earlier is that passive NOx absorbers is another technology that's been looked at to basically hold on to the NOx early on in the cold start or low temperature part of the cycle until the temperature heats up to a point where you can release it to the downstream SCR catalyst. These are working to basically, they're working on these catalysts to better separate those and get the temperature where you can hold it at a temperature just to the point where you can release it all to the downstream SCR, which is this selection here, where it's working, storage is working early on, and then the conversion, it's releasing it later on. And some durability work that's being done to show that these can actually last in longer terms, which is really a part that needs to be shown for a lot of these engines as we go to longer useful lives, is shown in this down here, that you have, when you age these systems, you actually can still see that the newest versions of these PNAs are operating almost at the same level, but very much less degradation after aging. The final idea I will just put out there is that packaging is also, there's a lot of work going on with packaging, getting things so that you have less heat loss, better thermal management. As I mentioned earlier, that natural optimization that's been occurring has already given us a lot of that. And there's even more that's being looked at as in combining some of the dosing into the DOC, which is shown in this type of device, where you basically can make things a lot more compact, have faster light off, bring the system as close to the heat source as possible. So just to summarize, multiple ideas and technology approaches are available to reach the ultra-low NOx levels that were the goals of the program. This engine, of course, has its challenges, being that it's a fairly cold operating engine. As was noted earlier, there is another phase of this or stage that will look at a different engine that is likely to have a better temperature profile. But there's certainly going to be, there's significant potential to get to much lower NOx levels from all types of engines right now based on the work that we've seen. So with that, thank you very much.
Thank you, Mike. Just first question from me is, can you give us a quick briefing on what the next phase is? Where do you see this research going next in terms of what MECA is involved in, or Southwest Research with Aerosols Board? Where are we with the program?
Sure. Well, so as we said, I think Bill had a slide up earlier that showed that there's currently this stage 2 work that's going on that's really outside of some of the work that we're doing, which is really just developing these low load profiles to have a test cycle that you can then test on as well to demonstrate that there's low NOx levels being hit there. The stage 3 that they're working on includes a different type of engine that may have the ability to use different types to demonstrate that there's different types of systems that could be used to get to low NOx from that. There's the natural transition then, of course, is to start looking into the non-road sector, where you could, that's traditionally been where the on-highway work has gone over the years. So there could be some work to demonstrate this from those types of engines in the future as well.
Thank you.